Hello students, we are in additional exercise problem 7.22 of chapter 7. We have 5 questions given. We will be dealing with this 5 one by one. Very first is, in an AC circuit, is the applied instantaneous voltage equal to the algebraic sum of instantaneous voltage across the series elements of the circuit? Is the same true for RMS voltage also? So let me explain the question first. Consider a circuit with resistor, inductor and capacitor in series, and this series combination is connected to some source of alternating voltage. Now at some point of time, if I see that voltage across resistor is VR, voltage across inductor is VL and voltage across capacitor is VC, can I say V is equal to VR plus VL plus VC? Yes, we can. We can say that voltage across resistor plus voltage across inductor plus voltage across capacitor is equal to total supplied voltage, but this is for instantaneous value. The same statement becomes false if we are talking about RMS voltage, because RMS voltage is voltage for one full cycle, and then you will have to consider phases also. And as these three voltages have different phases, we cannot say that Vrms of resistor, Vrms of inductor and Vrms for capacitor, if we add up, we will get supplied voltage. So it is true for instantaneous voltage, it is not true for RMS voltage. Moving to second question, B. A capacitor is used in primary circuit of induction coil. Why? In any inductor circuit, if we, sorry, in any inductor circuit, whenever we switch on or switch off the power, large back EMF is induced. And if we connect a capacitor somewhere, the back EMF will charge capacitor. And if you don't use capacitor, the back EMF will produce spark. So it's preferable to use capacitor in order to avoid sparking during switching on or switching off of such devices where you have high value inductor is connected. Induction coil is one of such device where high value inductor is connected. So to avoid spark, capacitor is used. Next one, C. An applied voltage signal consists of superposition of DC voltage and AC voltage of high frequency. The circuit consists of an inductor and a capacitor in series. Show that the DC signal will appear across C and AC signal across M. So here we have superposition of AC and DC. Suppose if I plot V versus T graph for same direct voltage, it would look like this. If I plot V versus T graph for AC, it would look like this, or if it is cos, the beginning may be different. Now when you superpose the two, AC and DC, the resultant voltage would look something like this. Okay, so this is superposition of AC and DC. Now the circuit which we are talking about is series combination of inductor and capacitor. So this circuit we are talking about, and I'll avoid using the source symbol because it is combination. But what essentially happens here is, when we are talking about the inductor, we know that the inductive reactance can be given as XL, which is omega L. So for AC component, this is 0. So inductor, for DC component, omega becomes 0, and then you don't have very much reactance from inductor. So DC will not appear across inductor. DC component will not appear across inductor. Instead, it will appear largely across capacitor, because if you take omega to be 0, XA will be infinite. So DC component will appear across capacitor and AC component will appear across inductor. Moving to next one. A chalk coil in series with lamp is connected to DC line. The lamp is seen to shine brightly. Insertion of iron core in the chalk causes no change in the lamp's brightness. Predict the corresponding observation if we have AC line. So earlier we had this problem discussed in one of the exercise problems. Suppose if we have a bulb means basically what we are talking about is high value resistor. So a bulb is connected with inductor, and what if I have DC? So when I have DC, as mentioned here, omega is 0, so inductive reactance is 0. It makes no difference uh, to this circuit whether inductance is of high value or low value, because inductive reactance will be 0. So when you insert iron rod here, actually it is changing inductive reactance, but for this circuit inductive reactance is of no importance and hence brightness will not change. On the other hand, think about a situation where this inductor and bulb combination, the resistor combination, is connected to some AC supply. What will happen then? Okay, in that case, this inductive reactance is important because you have omega present, and now if you insert iron rod here, you are changing XL. So what will happen if XL increases? Current in the circuit will decrease and brightness will decrease. So for DC source, nothing will happen if you insert iron rod in the inductor, but for AC source, inductive reactance increases, current in the circuit decreases, and hence brightness decreases. Next one. Why is chalk coil needed in the use of fluorescent tubes with AC mains? Why can we not use ordinary resistor instead of chalk coil? Very interesting question. The answer is fluorescent tubes require comparatively less voltage, and then if you wanted to get less voltage, you will have to consume extra voltage elsewhere. So we have two options. We can use inductor in series with fluorescent tube, or we can use resistor. Both can do that job. The only advantage of using chalk coil, that is inductor, is inductors will not waste energy. If you have resistor connected, the extra voltage will produce heat energy. That energy is lost. Instead, if you use inductor, the energy will not be lost, and that is the purpose why chalk coil is used instead of resistor. Okay.